Hi, welcome back to the statics review sessions. In this session, you'll learn about trusses, how to design a truss, how to find the members, and whether these members are on tension or compression. Trusses are structures that are used for bridges, for roofs as part of a roof, and also in some of the equipments like cranes. They are mainly composed of members that are connected at their ends with a pin to make them like a two-force members. Main assumptions are that the external loads or forces are always acting at the pins, trying to avoid that the loads are acting at in between the pins, so to avoid having bending or bending moment. Another assumption is that the weight of the members is neglected due to the fact that the weight as compared to the external loads are very low to be neglected. Members are, as we said, connected at a pins at both ends, which makes them two force members that are either under tension or compression. A design of a truss member is mainly to find what is the force magnitude in the member, and whether this member is under tension or compression. The way for the design is there's a method called the joint method, which taking a cut or disconnecting a joint like joint B, for example, and where this joint shouldn't have more than two unknowns. Um, because this will be considered as equilibrium of a particle, or this is coplanar concurrent force system, where you have only two equations of equilibrium. Forces in the x and in the y are equal to 0. You apply them to get the magnitude of the both members, and then decide whether these members is under tension or compression. So how we do that? After finding if you give an assumption that this force is going towards the joint, and then the calculation shows you that this is a right assumption. So going towards the joint, if you cut the member or disconnect it, you will have two forces that are equal and opposite in direction. So if that member is under compression, which means that this force will go towards the joint, and if it's under tension, then it will go out of the joint to have the member under compression tension. So if the calculation shows that this force is going towards the joint, then this we can just say that this is compression. If it's coming out of the joint, then this is tension. Another two important comment, which is before you start any calculations, if you see, notice that there are, for example, two members that are not collinear, and here collinear means that they share the same line of same axis line. So if, for example, A, B, and B, C members, these are collinear member. So if this non-collinear members, two members that are non-collinear, and there's no external forces, then you can say that these two members are zero members. So which means the magnitude of that member is zero. This is also a non-collinear member. They don't share their axis, don't share the same line, and there's no external forces. Then this is a zero member. Why do we use then zero members? Is for stability purposes. If there's any unforeseen forces coming to the structure, then these members can take these forces. For economical also reasons. So, for example, this the another type of zero members, if two members are collinear, like ADC, uh, and one member is non-collinear with them, AD, then this member is a zero member. So AD is a zero member. Also the same case here, you have two collinear members, and one non-collinear, and there's no external forces, then also AC is a zero member. If you just imagine that these two members, because they are zero, remove them, this will collapse right away because it's connected with pins, so it will collapse. It will be unstable. So, or to make it stable, then you would use a one long member from E to B, which would be not economical for the weight of the member, the cross section, transportation, and all of that. And to avoid that, using smaller members, but disconnect them and then connect them with these zero members. Notice here that this here is not zero members because of the, if you compare this with that, you have here an external force P, which makes it not a zero member. Both of them are not zero members. So, but in that case, because you don't have, so always when you start, try to look for zero members. It will reduce the calculation steps. The other methods, which we will go with an example in detail, it's called the section, a method of sections, to find the magnitude of the forces in members. Method of joints is that you, as I said, like you have to take a cut in a member in a joint that has no more than two unknowns. So we can start here. For example, this here has three unknowns. You can start here, apply equation of equilibrium. You can find this, and then you move up here. You reduce the number of unknown to two, and then you move continue. But method of sections allows you to find the unknown without the need to move from very far to get to it. So, for example, here the question asks you to find DE, KE, KL, and KD. First of all, before you start doing, or you have to look first, do you see any zero force member? And these four members that you are asked to. The only possibility is that KD is a zero force member. And from where do we know that? Because you have two collinear, this is CD and DE, and one non-collinear, KD, then this is a zero member. So you can right away, without the start of calculations, you can right away decide that this member is a zero. Let's see how many zero force members are they actually exist here, and you can do this as an just to as an exercise. First of all, let's start from the very far on. If you look at this member, so this force, if it weren't there, then this would have been a zero, both of them. But having this vertical will be only resisted by this member, which means that this member has nothing to resist, and if you apply equation of equilibrium, then you have this is a zero member. So ME is a zero, this is 1. 2 collinear, 1 non-collinear, MF is 0, this is 2. This is not a zero member because you have the reaction of that force and non-collinear, and you have another force, so you can't say that this is a zero force member. This we decided that this is a 0. This is also a 0 because looking on that side, you don't. If you look on that side, it won't tell. But if you look in this side, at this joint, 2 collinear, 1 non-collinear, then this is also 0 force member. This is also a 0 force member, and then 2 collinear, no external, then these two are also zeros. So you have 1, 2, 3, 4, 5, 6, 7 members that are 0 members. But it's used to for stability of that of the system, economical, and many options. So imagine if this is wasn't there, then you would have had to have like a very long and member, which might be uneconomical at all. So following step, we need to find these 3 members. We take a cut in there, just disconnected into 2 pieces, the whole structure, the whole truss, disconnect it into two pieces, and then we decide after which side would we work with. Is it the right hand side or the left hand side? If we decide to work with the right hand side, you notice that there is a support reaction there that you have to work with. Then before taking the cut and drawing this section alone, you have to find first the support reaction. So finding the support reaction comes from the whole system. Please, this is an important note and a mistake that always happens. Some would just take the cut and without solving that, and then when they draw this, they get stuck because they will have too many unknowns. Notice that when you take the cut, you have to see now the reactions of these members. So always find us. If the question asked to find these three members, then you could have cut there and then found without the need to find any support reaction. You worked on that right hand side. But so we need to cut there. So before we find the support reaction at Ly, that is part of the side that we would work with. You decide either side to work with. Always decide the side that is shorter, that has less external forces, that has less support reactions to work with. So we decide to work with the right hand side. To find that, some of the forces in the vertical won't help because you will have two unknowns, Ly and Iy. Some of the horizontal, of course, won't help. Then obviously some of the moments about the point to get most of the unknowns away, which is moment about I. Taking the counterclockwise as positive, then we just list the forces. You have Ly multiplied by the moment arm perpendicular from the point of rotation to the line of action of the force. These are the three bays, which is the 45, and then rotating positive, and then we can go from the left here that 25 times extended perpendicular to the line of action. Please, the distance is always the perpendicular to the line of action, never the one that is parallel to it. So you have 25 times 15, and then 55 rotating clockwise negative, then times also 15, and then you have 30, that force multiplied by the moment arm, which is 1 2 3 base times 15 is 45, rotating clockwise negative about the point I, and then you have this 30 multiplied by moment arm extend line of action, and then this all is the moment arm perpendicular to it, so it's 5 base times 15 is 75, rotating negative, and then finally this 50 multiplied by 5 base times 70 times 15 is 75, rotating counterclockwise, which is positive. We solve now, we have equation with only the Ly, and then you solve it, you get that the Ly is 6.67 kilopound or kip. Now we have that. The following step is to take the cut and disconnect the rest of the system. So you have only that system, half of it, and then following by that, drawing the unknown forces, which is in that case are the forces, the member forces. So you have a system with three unknown. Apply equation of equilibrium. This is an equilibrium of a body. So it's a concurrent, it's a coplanar non-concurrent system, three equations of equilibrium. So I would always try to look for the equation that would eliminate as many unknown as I want. So for example, if you look at point E, you can just apply equation moments about point E where you get rid of these two because they just pass through the point of rotation. They're not doing any moments. The moment arm is 0. So I will start with the moments about point E. Also, you get rid of this 30 and Ly because their line of action passed through the point of rotation. So then you will have only that KL also counterclockwise is positive. So KL is rotating negative and multiplied by moment arm that is perpendicular to the force line of action, the 12, and then 50, which is this force, multiplied by, you're taking a moment about this point, so multiplied by these two bays, 30, rotating positive, and then 30, that force multiplied by moment arm, which is perpendicular to this line of action, is 30. Also notice when we drew the forces, you just give any assumption. I give the assumption that are going out of the joint, which means that there should be tension. And then if you get a negative answer, it means that you have to change the direction. So now we have that. We solve it. You get its KL is 50 kip, or it's a positive 50. Please be careful. Here, positive 50 means that you give the right assumption. So you don't need to change the direction of that. So, which means that if this is coming out of the joint, then we said that this should be tension. Here's how you should write the answer, whether you write it with T or tension, but it's very important to write whether this is on tension or compression. Never learn it that because it's positive, it's tension. No, you will see shortly that it could be also positive, but can be compression. So again, the steps, you get the answer positive, right assumption, then going out of the joint, tension. So let's see how we found that. We need to find these other two. The following is I would just try to find a point that where I can eliminate as many unknowns, or so here when you eliminate these two, I extended the line of action and I got to a point K in the whole system, which is far a part of 15. If there were a force here in a system, you don't add it. You're just extending the line of action. You're not including anything in a system that was at this point. So you have these two line of action extended, and then you can take a moment about this point to avoid having these two in the equations, and then I have only this dE. So write equations of equilibrium, moments about K. Positive is counterclockwise, so we have dE multiplied by extend a line of action, drop a perpendicular. The perpendicular distance is that 12, and then you have the 50 times, multiply 50 times the 45, that's the moment arm, so it is from point K and rotating positive. Then this 30 times also line of action perpendicular, this is the distance 45, and then the 30, that's 30, is just multiplied by the 15. All right, please, it's only the distance that is perpendicular to the force. Many do the mistake and would take the 12. It's the 15 is the correct distance, and it's rotating counterclockwise, so it is clockwise, rotating clockwise, so it's negative. And then finally the LE that we just found, which is multiplied by the 15 and rotating clockwise. You solve it, substitute for the Ly that we got. Now you see here we get a negative answer. So negative answer means that this should be on the opposite direction. So instead of going out of the joint, it should go towards the joint, which means it has to be compression. So your answer would look like that. That this is 45.3 kip kilopounds, and it is compression. Notice the difference that they both were first assumption coming out of the joint, but one of them is negative, so you have to change it. Again, negative doesn't mean that it has to be compression. It's only because I give all the assumptions coming out of the joint. Finally, I could use just forces in to get, this is the remaining last one. So I could use forces in the y direction to get that force. To get the force in the y direction, which means that I can use now the y component of that force Ke in the formula. Before doing that, I need to know the slope or the angle. Given is the 12 and the 15. So if you look at this triangle, 12 and 15, then I can find the hypotenuse with a calculation of the Pythagorean theorem that gives you that this distance is 19.21. So I could then write the equation, which means that I use the 12 over 19 for the vertical component. So this is Ke multiply Ke times 12 over 19.21. It's in the negative direction of the y. Then you have negative 30, and then plus 50, and plus Ly. You solve it. This is the Ly that we calculated, 667. And then you just find the Ke, that remember Ke is negative 534. Again, negative means it has, this is the wrong assumption. It has to be directed towards the joint. Towards the joint means compression. The final note, I wouldn't change the assumptions, because when you change the assumption, that mean it will confuse you if you like to review your answers, review the problems. I would leave it this way. Don't change it as long as you describe your answer and say whether this member is under tension or compression, then you're good. This wraps up the trusses design. Please be careful in the calculation. Again, the negative, the moment arm, the also and another tip or note. Try not to use like equations where you have unknowns that you calculated to find others. For example, I could have first found some of the forces and got this Ke, and then I got that KL, and then you go sum of the forces in x direction to find dE. The problem with that is that the sum of the forces in the x direction, you will have 1, 2 that you already have just found before. If you have a mistake in any of these, then obviously dE would be wrong. So try to use the equation, try as possible, that has only this one unknown that you need to find. So as in that case here, here obviously I'll use the Ly. So but like if you use the if the calculation of Ly wrong, then you have both here are wrong. And yeah, here also, and that's why I picked also that moment, and then I picked the sum of the vertical to find this unknown. Thank you again, and see you in the next session.